Hey, I'm Chris Parsons, and in this video I just wanted to spend a few minutes discussing large model support. Often when I'm talking to developers and data scientists who are working with increasingly complex machine learning problems or larger datasets, we'll quickly end up discussing the out-of-memory compute problem, where they're constrained by or have run out of GPU memory and are unable to train their models. But there's a way around it, and I just wanted to show you how LMS, or large model support, can quickly solve this challenge. Let's take a look at this worked example. This is the typical as-is scenario. This purple box represents GPU memory, where our developer has to fit everything they need to train their ML model. We can see the input files, network definition, and the tensors, or computed output at each layer, must fit inside the available GPU memory. Now let's suppose we start working on a more complex problem using increased resolution images, a more complicated model, or even a large batch size. As we flow through the network during the feed-forward phase, we compute each tensor, which takes up space in the GPU memory. This is fine for the first two layers, but as we reach the third layer in the neural network, we've no longer got space to store the tensor, and we hit the out-of-memory error, which typically causes our training to fail. A bit like when your Mac beach balls or you get that dreaded blue screen of death. Large model support provides an alternative to this problem by paging the computed tensor out to the relatively inexpensive system memory during the feed-forward phase. As you can see, this frees up GPU memory for each subsequent tensor, alleviating the out-of-memory error we were seeing before. As we compute the final tensor for the bottleneck layer, we calculate the loss and begin backpropagation, loading each previous tensor into GPU memory as we need it, thereby preventing the system from running out of GPU memory and allowing us to work with larger datasets, increases in batch size to improve training times and accuracy, or even more complex models. But how can we make this happen? Surely everything slows way down because of the interconnect between the CPU and the GPU, right? Well, this representation of an x86 derivative architecture illustrates that bottleneck. While the GPUs are connected over NVLink, the CPU, which is required to transfer the data from system memory, is communicating with the GPUs over PCIe. With IBM Power Systems, the architecture is designed specifically for machine learning workloads. Through collaboration with NVIDIA and others, the NVLink high-speed interconnect technology has been added directly to the processor silicon. This means we can move data between system memory and GPU memory at 10 times the bandwidth you can anywhere else. It's this that makes large model support possible. What we see here is the NVIDIA profiler view of training one MRI scan through the model. The top is PCIe utilization and the GPU utilization is shown here. It took the PCIe connected GPU 2.5 times longer to process the same image. Again, a few of those corresponding kernels that represent GPU utilization are the same, right? Because it's doing the same work. But what's been alleviated in this chart is the time the GPU spends waiting for the data to be transferred via PCIe. So if you check the description of this video, you'll find out lots of useful links to blog posts and articles describing LMS in more detail. And if you stay tuned, you'll find a tutorial explaining how you can adapt your TensorFlow model to take advantage of LMS today. Thank you very much for watching.